This then is the unit at the heart of McCullough's vision. It's his simplification of the idea that he has that a neuron might act as a simple computational unit within a network. The McCullough-Pitts model neuron here will feature as the basic computational unit within all the models that we're going to look at. I'm still using the term neuron because I want to make the link to McCullough explicit, and we will drop that term later on because, as you'll see, this element has very little in common with an actual neuron. The basic model is very, very simple. A unit within a network receives input from other units, which it sums up. That's the sigma, capital S in Greek. It sums up its inputs, and then it takes that sum, which is called its net input, and it uses it to calculate a value called the output, which is associated with this unit and which will then be passed on to other units. We refer to this value as the unit's activation. Here it's given by y with the subscript I. So let's have a look at this in a bit more detail. Our starting point of a vision of a model of a neuron has now been reduced to a single unit or node that computes its net input as the weighted sum of all incoming values. So the sum here, now we're going to look at the sum consists of the activations of other units, that's y sub j, multiplied by the weight linking that unit to the unit who's calculating its sum, that's the weight wij. We add up all those to get the value net sub I and use that to calculate the output value of this unit, which is its activation. Let's go over that in some detail. To calculate its net input, the unit must be conceived of as sitting within a network and receiving values, activation values, from other units. Old habits die hard. The link between the preceding units and the current unit is given by a weight. And we need to introduce a convention here, and we'll stick to this convention, and this convention is ubiquitous in the field. It's not just for the purposes of this class. When we say wij, we're referring to the weight to unit I from unit j. So the sum consists of the activation of this unit multiplied by the weight connecting it to our present unit, unit I, plus the activation of this unit multiplied by the weight connecting it to unit I, plus this unit multiplied by its weight. Or more concisely, the formula is given there in the bottom right-hand corner. The net input to unit I consists of the sum of the weights multiplied by the activations of the feeding units. So, having calculated our net input, we then need to calculate the activation of this unit, of unit I. This is called the activation function. So it takes one value, net sub I, the net input. Net sub I is the term we use to refer to the net input. It takes that value and returns the activation as just a function, like y equals x squared is a function. If you take the value 2, y equals x squared returns you the value 4. Now, the simplest function we could imagine here is the identity function. It does nothing. So you give me the net input and I will set the activation or the output of this unit to be the exact same thing. Here, there is an activation function, but the activation function is the identity function. We will meet such units. They're not very common. And we will call them linear units because the relationship between the activation of the unit's output, and its input is a straightforward straight line, y equals x. Far more commonly, however, units will employ what we call a sigmoidal activation function. This is a nonlinear function seen on the right-hand side of this figure. You can see it's an S-shaped function. The x-axis here tells you what the net input to the unit is. It can lie anywhere from minus infinity to plus infinity. And the output of this unit will lie somewhere between 0 and 1. That is, for very negative inputs, we will always produce something very close to 0. For very large inputs, we will always produce something close to 1. The S shape of this function is very, very important. The actual details of what the mathematics is to produce this S shape are not terribly important. You can see the mathematical definition of this particular S-shaped function at the bottom of the slide, 1 over 1 plus e to the minus x. If you've never met those things before, e is a particular number between 2 and 3, which plays a big role in logarithms and exponential functions. It's just a number, like pi is a number or 3 is a number. You don't have to do this calculation. Well, we'll do a little of it just to try it out in the first lab, but basically the machine will do all this. The important thing to realize is that the unit is producing an activation which is bounded. Because of the form of this particular function, it's bounded between 0 and 1. We could use other activation functions. We could use similar S-shaped functions with different ranges. And we could use non-S-shaped functions. These have all been tried out. But by far the most common activation function found in most neural networks, certainly of the kind we'll be looking at, this S-shaped function is used, which is bounded by 0 below and 1 above. So looking at the architecture on the left, in panel A, assume that the output unit is a unit which has this kind of activation function. It will first compute its net input, which will be 1 multiplied by minus 0.25, plus 1 multiplied by 0.6. That gives the net input. That gives a point on the x-axis, and then we read off the unit activation on the y-axis. We will meet other activation functions. In the software we're using, all units have this particular sigmoidal activation function, so we're not going to care too much, but it's important to realize that one of the choices a modeler has is to employ different activation functions. But they're all doing the same general thing. We sum up the inputs and we compute a nonlinear function of the outputs. So far we've only spoken of a single unit. The units within a network are grouped into layers. And here we're talking about the network as a whole and not an individual unit. The first layer of units is the input layer. The values associated with these units are provided by us. These are our inputs. They constitute a data set that the network is working with. The final layer is called the output layer of the network, and this provides the result of the computation. Between the input layer and the output layer, we usually have one or more so-called hidden layers, and we'll see the reason for these as we go along. So, the modus operandi, the way a feed-forward network works, is like this. I'm showing you here a basic 3-layer feed-forward network architecture with the input layer at the bottom, the output layer at the top, and the weights between the units shown by the lines. In the computation of a single output value for this network, we start by providing some input. Here the input pattern has 4 numbers, 0.5, 1, minus 0.1, 0.2. They came from us. We, the modelers, have chosen to ask the network to compute some transformation of these values. They don't mean anything unless they mean something to us. From the network's point of view, they are just these numbers. Now, the units in the hidden layer all receive input from this input layer, and they calculate their net input values, calculate their activation functions, and the result is shown there. So now we have values at the hidden layer, and now we can repeat the process for the output layer. They will compute their net inputs, compute their outputs, and so we have a mapping now. We've gone from our input pattern, this network has produced that output pattern. The exact values that are produced at the output layer are going to depend critically on not only on the input pattern, but also on the weights within the network. That's it. That's the basic mode of operation of pretty much all neural networks. There are details that get changed here or there, but there's no magic, there's no neurons, there's no brains, there's just these little sums being done. And the whole business starts with numbers, which we provide, and it generates numbers which we interpret. The interpretation of these numbers is the researcher's responsibility. The network does nothing but sums. It is the equivalent of a calculator or a slide rule. The interpretation of the inputs and the outputs belongs with the researchers. It's very important that you understand these computations that are at the heart of every neural network. When you are clear about these, you will be less likely to attribute magical properties to the network, and you will recognize better the division of responsibility between the network which does sums and nothing else, and the researchers who, first of all, gather numbers to present to the network, and then interpret the output of the network in one way or another. That's the secret. That's the magic sauce.